Hello and welcome to this talk on how the Fourier transform is used in digital communication systems. Okay, a quick introduction to orthogonal frequency division modulation and orthogonal frequency division multiple access. A lot of words there. Okay, so this little talk has come about as a result of a question that comes up fairly regularly during my digital signal processing course at the University of Oxford. And often engineers and scientists on the course have heard of OFDM, OFDMA, Fourier transforms, but don't know how these different components connect together and work together. So I often end up sort of ad-libbing an answer. I thought I'd just sit down for 10 minutes and discuss it. So orthogonal frequency division multiplexing, or OFDM, is much easier to say. OFDM is a multi-carrier modulation technique. In other words, instead of having a single sinusoidal or cosinusoidal wave that we're modulating with amplitude and phase, we are going to modulate multiple carriers at the same time. So we are going to take our available spectrum, for example, a 10 megahertz carrier, a 10 megahertz bandwidth signal on a carrier, and we're going to divide that into orthogonal subcarriers. So if we have in our frequency space, we have our central carrier FC, then we have our bandwidth, and we, instead of transmitting over the whole bandwidth, we're going to transmit lots of separate subcarriers within that bandwidth that we are allowed to transmit. So, for example, if the bandwidth is 10 megahertz, then we have, for example, 1,000 carriers. N equals 1,000. Of course, the bandwidth per carrier is 10 megahertz divided by 1,000, which equals 10 kilohertz. So each carrier is quite narrow, especially if we're talking about gigahertz for 4G, 5G comms, Wi-Fi, etc., etc. Each of those carriers is orthogonal. In other words, any variation on one of those carriers will not, fading, any kind of interference will not directly impact adjacent subcarriers. There are many reasons why we would want to use this technique. A good example is in digital subscriber line, cable to the home. If we have some interference from some local radio, transmitter, something like that, if it's knocking out a few of the carriers, it doesn't matter, because the rest of the carriers will carry on working perfectly well. So it's very robust to multipath fading, noise, and it's very spectrally efficient because we're using the whole spectrum, divided up across our subcarriers. OFDM is typically used in applications such as DSL, where you have one modem, one router in the house connected to one modem or receiver, transmitter at the local exchange. So it's a point-to-point link, single user with a single connection. The transmitter in each direction uses an inverse Fourier transform, and the receiver uses a forward Fourier transform. So let us see how they work together. That's shown here. So if we just think of a very simple example where, for example, we have eight carriers, yes, with slightly different colors. We have a channel. If we think about, just visualize the inputs being in the frequency domain here. So we're turning frequencies on and off. The inverse Fourier transform takes all of these frequencies, modulates them separately, and then converts them from the frequency domain to the time domain. So we have one array coming out, which is our time domain sequence with all of our sinusoids and cosinusoids. We transmit that down the channel. Then we need to take our forward Fourier transform to convert from time back to our frequencies, and we're back to the original signal. So for example, if we are just modulating very simple BPSK, binary phase shift keying, we've got zeros and ones, we could have that sequence, random sequence. We modulate that to a bunch of sine waves and cosine waves that are either on or off, and if everything's working correctly, coming out of this end, we have exactly the same sequence. And so for each time we send a frame, we can adjust the specification, if you like, for the input frequencies. That changes our sinusoids and cosinusoids that are transmitted over the channel. It could be a wireless channel or any other channel. Then we convert at the receiver, we convert those time domain signals back to the frequencies, and we look at the outputs. Now this is just a simple example with binary phase shift keying. We can use much more complex modulation schemes, typically higher order quadrature amplitude modulation, where each of these carriers carries 3, 4, 5, 6, 8 or more bits every time a frame is transmitted. So that's how OFDM works. Actually, over a frame will transmit more than one symbol, but that's getting into too much detail for this discussion. So we're going to transmit the the data from the user to the end receiver. Now, the question becomes, how do we know what this channel is doing to our data channels? And the answer to that question is that actually we use pilot channels to transmit known reference symbols from the transmitter to the receiver. And these known reference symbols are used for synchronization, channel estimation, i.e. fading, noise, all that kind of stuff, and channel equalization at the receiver. So basically, we're going to transmit a known sequence all the time on certain carriers, and the receiver knows exactly what it should receive. And if it doesn't receive those, it can then calculate what fading, filtering has happened on that channel and compensate for it. But there's slightly more to it than that. So let's just say, I'm going to choose a different color. Let's just say this channel, we're going to send a reference sequence 0110. And this channel, we're going to just send a reference sequence 1001. At the receiving end, we should receive those signals. So it'd be 1001, and over here was 0100. But of course, the channel will, in the analog domain, will have modified the signal somehow, filtered it, faded, blah, blah, blah. And it would also have modified the channels in between our reference carriers. So basically what we do, we take the knowledge from these reference carriers at the receiver, we then interpolate them across the data channels. And so now at the receiver, we can compensate for any impacts of channels and so on across the data channels, even though we're not sending our pilot tones down the data channels. Because we send the pilot tones on a nearby adjacent channels, we can interpolate the variation across our data channels, and we can estimate what the fading is, etc., and compensate for it at the receiver. So that's a very, very high level of OFDM. The extension to that is to go from a single user to multiple users, and this is where we have orthogonal frequency division multiple access referring to multiple users. And essentially what we now need to do is split the modulator demodulator into separate operations and multiply accumulator, a MAC layer, media access control layer, and a physical layer. And if we go back to our previous discussion, how that works is that basically the MAC layer sits above or in front of and behind the physical layer of the transmitters and receivers. And now the two MAC layers talk to each other, again, over channels. They might allocate dedicated channels for communication. And now what happens is, if we have user 1, user 2, just very simply, then basically they both talk to the MAC. The MAC might allocate certain carriers to user 1, and then user 2, let's use a different color, we'll use green. User 2 gets these carriers, and so it's got a higher bandwidth overall. At the receiving end, the receiving MAC knows that these carriers are used for user 2, and so user 2 gets its data out like that. And that sort of negotiation, management, that whole process, managing users' bandwidth, multiple users for handling different data formats, for speech, for video, for an ordinary telephone call, voice over IP, whatever, web surfing, all of that sort of thing, all of that's handled at those higher layers. And the MAC media access control layer is one of the key layers that handles that process. Okay, that very, very quick rundown. There's some examples of how OFDM and OFDMA are using. Thank you very much for your time. Hope you found this useful. Please do put some questions below if you do have any. Thank you very much, and goodbye.